Welcome back, ninth grade science students. Today we're going to be talking about mechanical advantage and efficiency. Alright, so the opening slide, we have a nutcracker. You might be asking yourself, okay, what is mechanical advantage? Well, mechanical advantage is a machine that's going to help make work easier for us. So if we're looking at this thing right here, if you try to just grab this and go like that and go like that, you're going to have a hard time. But let's just say at point B, and if you squeeze the handle right here with 5 newtons of force, let's just say at point B, you're going to get 20 newtons of force right back out. Obviously, you can see it multiplied the force, and the mechanical advantage at point B would actually be equal to 4. So the AMA, which we'll talk about later, is equal to 4. So the actual mechanical advantage is equal to 4. Now at point A, you guys probably know how this works. You're going to get a lot more force at point A. So let's just say at point A, you get 30 newtons of force. So then think about, what would the AMA be? Well, hopefully a lot of you guys said it was 5. So it multiplied, 6. Because it multiplied the force by a factor of 6. So all we had to do is put in 5 newtons of force, but then here we're getting 20 newtons, and there we're getting 30. That's the mechanical advantage. And in this section, we're going to calculate the mechanical advantage. Alright, so let's keep working. So here's the vocab word. Mechanical advantage of a machine is the number of times that the machine increases an input force. So it's the number of times it increases it. So if you look at the previous example, if we put in 5 newtons of force, we got 20 out. The mechanical advantage was 4. If we put in 5 newtons of force and we got 30 out, the mechanical advantage was 6. So it's just the number of times that it increases the force. So, which brings us up to the actual mechanical advantage. Now today, we're going to learn about 2 types of mechanical advantage. One is going to be actual, and the other one's going to be the ideal mechanical advantage. The ideal mechanical advantage will be without friction. The actual mechanical advantage includes frictions, like what is happening in the real world. So maybe let's put a star in our notes and let's say the actual mechanical advantage includes friction. So it's like literally what is the actual advantage. The formula to calculate the actual mechanical advantage is the output force divided by the input force. So if you're thinking of the nutcracker, the one example was we got out 20 newtons and we put in 5 newtons. So the mechanical advantage was 4. That's how you calculate it. It's that simple. You just have to know the output force and the input force. So let's look at a car jack, because the last lesson talked about how simple machines make our life easier. So let's just say a person used 5 newtons of force on the car jack. The jack then puts 1,000 newtons of force on the car. Calculate the AMA. Alright, so the AMA is output divided by input. So when you read through that, you can see this is the output. That's what we're getting out of the machine. The 5 newtons is the input. So then you just divide it. So 1,000 divided by 5. So then you're going to get 200. So that is a really good simple machine. You're getting a lot of mechanical advantage. So you guys can see that probably the higher the number that you calculate, the better the machine is. So like with the nutcracker, we got 4 for mechanical advantage. With a car jack, we're getting 200 for mechanical advantage. So the higher the number, the better the machine. So here's another one for us. Let's say we test the machine and you find that it exerts a force of 5 newtons for each 1 newton of force you apply to it. So this would be the output and the input. So you just take 5 divided by 1. It's pretty simple. So the mechanical advantage would be 5. Alright, let's keep working. So that was the actual mechanical advantage. That's like including friction, because actually let me explain that a little bit more. So obviously the Nutcracker isn't a frictionless, simple machine. At this pivot point, we're going to be losing some energy. We're going to be losing, some of those forces. But so that's the actual mechanical advantage. We looked at, okay, I put in 5, I got 20. So that's the actual, including friction. The ideal mechanical advantage would be like in a perfect world, like if we could make that Nutcracker totally frictionless, so like a really, the best ball bearing in the world at that pivot point, that would be the IMA. So we abbreviate it IMA, okay? And this includes friction. This includes the friction. Excuse me. No, this one excludes friction. So in a perfect world. All right. So how do we calculate that then? Well, the IMA, instead of looking at the input force and the output force, that's the actual mechanical advantage. For the IMA, the ideal mechanical advantage, we use the input distance divided by the output distance. So let's look at an example of calculating this. We have a woman drives her car up onto wheel ramps to perform some repairs. If she drives a car a distance of 1.8 meters along the ramp to raise the car 0.3 meters, what is the ideal mechanical advantage of the wheel ramp? Let me draw a picture so you guys can kind of see what's happening with this scenario. So there's the wheel ramp. I'll just draw on a tire. She's gonna drive it to the top of this thing. Now let's make it more flat. Give me 1 second here. Let's go like this. There we go. That makes more sense. Okay. So she's gonna drive a distance of 1.8 meters, and it's going to raise the car 0.3 meters. So we're going to calculate the IMA, and the IMA, we're going to need the input distance divided by the output distance. So if you're thinking about this wheel ramp system, what is the input distance? Isn't this right here? Yep, the input distance is how far she's putting into the ramp, which is 1.8. What's the output distance? Well, that's what you're getting out of the machine. In this case, it's raising the car for us 0.3 of a meter. So the input distance is going to be 1.8 divided by the output, what we're getting out of the machine, 0.3. So then we're going to get 1.8 divided by 0.3. So then the IMA would be 6. The IMA would be 6 for the wheel ramps, which is actually a pretty good mechanical advantage. So this is saying we're ignoring friction altogether, right? In a perfect world, the IMA would be 6. And the same thing goes with the IMA. The bigger the number, the better the machine, or the more mechanical advantage we're getting. All right, so let's try one more. There's another ramp. Let's find a different problem here. Yeah, let's look at this one. It says a construction worker moves a crowbar through a distance of 0.5 of a meter to lift a load 0.05 meters off the ground. What is the IMA of the crowbar? So I'm going to draw on a crowbar to give you guys a scenario. Let me draw on the ground. Alright, so there's the crowbar. And let's say it's kind of lifting up this box. There we go. So the crowbar is lifting up the box. What's the input distance? Well, you can see that it's going to move the crowbar 0.5 of a meter, right? It's going to be cranked down. So the input equals 0.5 of meters, and then because the design of the crowbar is going to lift this thing up 0.05 of meters. So that's going to be the output. That's what we're getting out of the machine. Alright, so AMA is input over output, and I should say distance. The input, we put in 0.5. The output, we put in 0.05. So we can calculate the ideal mechanical advantage of the crowbar, and I get 10. So this crowbar gives us quite a bit of mechanical advantage. It gives us 10. Now again, that's the IMA.
Sue or Linda, could you come see me in the office, please?
Alright.
Sue or Linda.
I think I'll skip this one. I'll leave you guys to do that.
Linda Burke.
So last thing we're going to talk about is efficiency. So what is the efficiency of a machine is always less than 100%. And you might be asking yourself, well, why is it always less than 100%? And some of you guys are probably going, well, it's because there's friction. And you're right. So if you think back to the nutcracker example, I'll go back to that. This thing is never going to be 100% efficient where we're getting the full mechanical advantage of it, because we're going to be losing some energy to the thermal energy at that pivot point. So the actual efficiency of the machine is always going to be less than 100%. Oop, I gotta fix this. Give me 1 second. Alright, I'm back. The iPad is doing its thing there. So yeah, so the percentage of the work input becomes some of the work output. It's going to be lost. It's going to be the efficiency of the machine. So how do we calculate this? Pretty simple. You just take the work that you're getting out of the machine, which is always going to be less, and you divide it by the work that you're putting into the machine, and then you multiply it times 100%. And then I'll tell you how efficient the machine is. So let's look at an example of this. So we have just designed a machine that uses 1,000 joules of work from a motor every 800 joules of useful work the machine supplies. What is the efficiency of this machine? Well, the 1,000 is the input. That's what you're putting in. That's your work input. Because remember, the work input is always going to be bigger, so that's a good way of remembering it. The output is always going to be less because you're losing some to friction. So just keep that in mind when you're doing these calculations. So efficiency is work input divided by work output. Oh, I'm sorry, it's the other way around. Because the output is always less. So that number is going to be on top, times 100%. So it's pretty simple. We're getting 800 joules of work out of this machine. We're putting 1,000 joules of work into the machine. So then for the mental math would be 8 over 10, which is basically 80%. So the efficiency of this machine is 80%. Obviously the goal of every engineer is to try to get a machine that is, greater than or close to 100% as possible. Let's see here. Let's look at this problem. Let's say we know the efficiency of the machine is 40%, and you do 1,000 joules of work on the machine. What's the work output going to be? All right. So we know the answer is going to be 40%, but I'm going to convert that to a decimal so it works. The input is going to go down on the bottom. We're doing 1,000 joules there, and what we're trying to find is the work output, so that's going to be our X. So then it's actually not too bad. You just take 1,000 times 0.4, so then X equals 400 joules. So just doing a quick summary here, you're putting 1,000 joules of work into the machine. Well, the machine's 40% efficient, So you're going to get 400 joules of work out of the machine. So I'll skip this one. So like I said, engineers are trying their best to try to have the efficiency of any sort of simple machine to be the best possible case. And so what could they do to make those machines a little bit more efficient? The best way is reducing the friction, because that's where we're kind of losing some of the work output there. So ball bearing systems, grease, oil, those types of things are put into car motors so that they be more efficient. On your roller blades, they put they've got ball bearings on them. Even something as goofy as air resistance, because air resistance technically is friction. So if you're going to be an engineer, this is something you would have to consider. And I remember when my wife was trying to buy a car, there was a goofy like little wing thing on her side mirror, and I was like, why does this thing just looks kind of goofy? And the guy at the dealership said, well, that actually serves a place and purpose. It increases the efficiency of the car, and it was like, it was a small amount, but it was enough to make the gas mileage go up. Alright, I think I'll leave these questions for you guys. You do have an assignment on 14.3 mechanical advantage. So just doing a quick summary. So what we talked about today, we talked about the actual mechanical advantage, which is just output over input force. That's where friction is included. We talked about the ideal mechanical advantage. This is the absent, let me go back to here. That would be like when the absence of friction. And we calculate that by looking at the input distance over the output distance. You guys might want to write down a list of formulas for this chapter. Let's see here, because there's a lot of them. We talked about efficiency of the machine, which is just the work output over the work input times 100%. So yeah, that's what I recommend doing is, write down these formulas. They're in a box for you here. Write them down so you have them for the homework. Alright, I'm going to let you guys get started on it.